Hello everyone and welcome to Coderific. In this video we will explore how the Gemini 1.5 Pro model handles fall detection using the smart fall dataset that is a challenging time series accelerometer dataset. More specifically, we will evaluate the performance of the model in both zero-shot and few-shot setups to see how effectively it can classify false versus known false. Along the way, we will analyze accuracy, precision, and recall and compare their confusion matrices. In description below, I have provided links to download the dataset and its associated research paper. If you want to know more about this dataset, how it was collected, then I will encourage you to go ahead and read this out. Let's dive in. In the first step, we install the Google Generative AI Python SDK, which provides the necessary tools to interact with Gemini 1.5 Pro. The -q flag ensures the installation process is quiet, reducing unnecessary output during the setup. Next, we import the Google.Generative AI module, which is part of the SDK we just installed. This library serves as the bridge to communicate with the Gemini 1.5 Pro model. We also use the user data module to securely fetch the API key required to authenticate our access. After retrieving the key, we configure the SDK using genai.configure method. This ensures that the model is properly connected and ready to process our prompts. Here in this cell, we initialize the Gemini 1.5 Pro model, which will be the core of our experiment. Basically, before diving into fall detection experiment, we want to test that everything is working smoothly. And for that, we test the model with a creative prompt to generate a short 50-word story about a magic backpack. Then we start by mounting Google Drive to access our dataset. After establishing a connection to my Google Drive, here I navigate to the directory where SmartFall 2018 dataset is stored. In this step, we load the training data from the SmartFall dataset. This dataset contains accelerometer readings recorded as 3D time series data, each labeled as either a fall or no fall. Labels are binary, 1 for false and 0 for non-fall activities. So here we want to make sure that the data structure and labels are correct and the dataset is ready for further pre-processing. Then we implement a sliding window approach. This technique breaks the time series data into overlapping windows, each containing 50 time steps with a stride of 25. This means each window is labeled as fall or no fall based on the proportion of fall labels within the window, using a threshold of 50% of overlap. This is the total number of windows that we get with shape of window size, that is 50, and 3 coordinates x, y, z for every data point. As you can see, this is a huge number of total windows, and in a scenario where we have limited number of tokens, we cannot proceed with all of these windows. So for that, we downsample the dataset by selecting an equal number of fall and non-fall windows. And this is necessary because the maximum number of tokens is less than 50,000. Therefore, we can use a maximum of 30 windows for training and testing in zero-shot and few-shot examples. As a result of downsampling, we get 30 windows for training. This subset will be used for examples in few-shot experiment and the same number of windows for test subsets. We will be using this subset for testing the model performance. And to be precise, in each subset, we have equal number of windows for no fall and fall class. Now that we have prepared our dataset, let's move on to our main experiment, starting with zero-shot classification. In this cell, we first format the test window into a prompt suitable for the Gemini model. Each window contains 50 timestamps with 3 axes accelerometer data, that is x, y, and z. The task for the model is to classify each window as either a fall or no fall. As specified here in the prompt, the model will return its predictions as yes for fall and no for no fall. Inside this prompt, the formatted data is passed into the generative model for classification. This setup includes fine control over parameters such as temperature and top P to ensure deterministic outputs. After running this cell, we have obtained the following output. As you can see, the final output needs a lot of refinement for post-processing. That's why in this cell, we extract the prediction of the model from its response text. Using regular expressions, we match the predicted labels yes or no for each window. These predictions are then converted to binary format to facilitate evaluation against the ground truth labels. By doing this step, we want to make sure that the predictions are ready for quantitative evaluation that will help us understand the performance of the model. After converting the predictions in compatible format, next in this cell we evaluate the performance by computing the classification report. This classification report provides a detailed breakdown of precision recall and FN score for both fall and no fall categories. And the confusion matrix visualizes the counts of true positives, true negatives, false positives and false negatives. So in this experiment of zero-shot classification, the model relied entirely on its pre-trained understanding to classify the data. And the output we got is 73% of accuracy. Finally, we visualize the confusion matrix for a more intuitive understanding of the model's performance. The matrix highlights the distribution of correct and incorrect predictions across the fall and no fall categories. And in this experiment, we got 13 true positives, 9 true negatives, 6 false positives, and 2 false negatives. This means that zero-shot approach errs on the side of caution, marking more events as false than necessary. Now let's move on to another experiment, which is the last experiment of this evaluation, and it is few-shot classification. In this experiment, majority of the process here mirrors the zero-shot setup, with one key difference: the inclusion of example windows in the prompt. To set up the few-shot examples, we format the training windows into labeled examples. These examples provide the model with context and a clear understanding of how to classify fall and no fall windows. Then in the prompt, we first introduce the labeled examples and then ask the model to classify the test windows. And we got response from the model in the same format as we got in zero-shot experiment. And this response can be refined by converting them into binary formats to facilitate the classification report and confusion matrix generation. As we can see here in the output that the accuracy has improved a lot from 73 to 87, which is about 14% increment. And if we closely look at the confusion metric, we can see that the few-shot approach eliminated false positives entirely, achieving a perfect precision score of 100%. But this came at the cost of missing some falls, as shown by the 4 false negatives. The recall dropped compared to zero-shot, indicating a trade-off between precision and recall. To wrap up, we have explored how Gemini 1.5 Pro handles the challenging task of fall detection using zero-shot and few-shot prompting. This experiment highlights the potential of Gemini 1.5 Pro to handle complex tasks like fall detection effectively and efficiently. Its ability to adapt through prompting strategies makes it a promising choice for intricate time series data analysis. Thanks for following along. If you found this video insightful, don't forget to like, comment, and subscribe to more deep dives into AI and its capabilities.